In the previous workflow, I had used the SAET tool to automatically extract the shoreline around Satabhaya in Odisha across 2 time periods 4 years apart. Subsequently, I had quantitatively measured the rate of change as well. I had done so by creating a 2 km long reference line parallel to the coast, splitting it into 10 segments of 200 meters each, and then measuring the average distance from the extracted shoreline points to the nearest segment on the reference line. The final output is displayed on the map here. In this video workflow, which is the 7th in the series, I will perform a more refined change analysis and even attempt predictive analytics using a recently developed tool called EPR4Q. But before that, let me quickly highlight the narrative and evolution of the techniques that I've covered in my previous 6 workflow demos on shoreline detection and analysis using remote sensing thus far. In the first workflow, I demonstrated a basic visual method using the historical imagery tool available on Google Earth software to spot the development of the shoreline over a period of time. While rudimentary in nature, this technique has a particular benefit. It allows a user to quickly gain a perspective of the area of interest, which is useful prior to deep diving with more advanced tools. In the second video workflow here, I had demonstrated a technique to do a better form of basic visual detection and trend spotting using a satellite imagery web interface called Earth Observation or EO browser. This platform allowed me to view the optical satellite imagery for the desired timeline over Marina Beach in Chennai, Tamil Nadu, and even visually delineate water from land using a water radiometric index known as Normalized Difference Water Index or NDWI. Subsequently, I was also able to generate a time-lapse video of the imagery across multiple timelines. In the third video workflow, I had gone one step further. I had actually downloaded the Sentinel-2 optical satellite imagery over the area of interest in Anjana Beach, Goa using the Copernicus browser. Processed it using modified and better water radiometric indices on the open source Snap tool here. And finally, also what I was able to do is to actually extract the shoreline over the 2 time periods using the premium but the trial version of ArcGIS Pro GIS software. In the fourth workflow here, I had downloaded for the area of interest, which is Vizag coast in Andhra Pradesh, a different type of satellite imagery from the Copernicus browser. This type of imagery is known as SAR or simply radar imagery, which has a unique feature in that it is able to collect the Earth observation information even at night and remains unaffected by weather conditions such as cloud cover. Subsequently, I had delineated land from sea by applying a set of geoprocessing commands and a digital elevation model or DEM based algorithm and refined it further by thresholding the reflectances. Even here, the shorelines were extracted using ArcGIS Pro. While all the previous 4 workflows were performed using satellite imagery from the European Space Agency's Sentinel platform, in the 5th workflow here, I have used a different source of optical satellite imagery, that is Landsat satellite imagery from NASA USGS platform. The area of interest remains the same, which is Anjana Beach in Goa, which I had used in the previous workflow. I had processed the Landsat imagery and on ArcGIS Pro using the tasseled cap technique, which involves the use of a vegetation index instead of a water index. The vegetation index is called NDVI, and I had used the vegetation index to delineate land from water. Finally, I had even compared both the output of the derived shorelines from Sentinel and Landsat imagery on Google Earth and shared my observations on which is better, what are the advantages and disadvantages. And finally, as I had indicated at the very beginning of this section of the video, in the 6th workflow, I had demonstrated a very handy tool, the Shoreline Analysis and Extraction Tool, or in short, SAET. It has been developed by European Space Agency under its ECFAS coastal monitoring platform, and it not only allows a user to automate the download process of Landsat and Sentinel optical satellite imagery by running a straightforward Python-based command, but also it allows us to run a custom algorithm to extract the desired shorelines over the area of interest from the raw imagery just as well. Our area of interest was in Satabhaya in Odisha, and the beauty is that the entire workflow from download to processing to extraction can be completed in just about 10 to 15 minutes, and it generates a consolidated breakage-free and a reasonably accurate shoreline for the area of interest. Post the shoreline extraction, I had even measured the rate of change across the two timelines by creating a reference line and performing distance-based quantitative analysis using the open source QGIS tool and refining the visual map-based output subsequently on S3's ArcGIS Pro platform. The seventh and final workflow that I'll cover shortly is the endpoint rate tool for QGIS or EPR4Q, a recently developed algorithm used in scientific coastal research. There are several other powerful tools which deploy similar or different techniques that are not covered in this series. Some of the notable ones are, beginning with perhaps the most popular one, the DSAS or Digital Shoreline Analysis System by USGS. Its methodology involves casting transects and then calculating the endpoint rates just as the EPR4Q tool. Unfortunately, DSAS only operates on a historical version of ArcGIS Pro, the ArcMap commercial software that I do not possess. The transects technique by itself is not too difficult to grasp. It basically involves taking two or multiple shorelines over different timelines. Subsequently, we have to draw a seaward and or landward baselines or reference lines parallel to the shore, and then we have to cast perpendicular lines onto the shoreline from the baselines. DSAS and EPR4Q tools basically are automated ways to cast transects over large areas at tiny distance intervals, which basically enhance the accuracy of the quantitative results. The rate of change, regression, and other types of statistics are calculated subsequently by measuring the distance between the transect intersection points on the shorelines considered. Besides DSAS, there is also the UMBUR, which is analyzing moving boundaries using R. It basically uses the R analytics package, something which I'm not familiar with, and hence I have not given a demonstration for this. CoastSat is another algorithm which is used in scientific coastal research. It's an open source software written in Python, and it can perform various different types of advanced analytics such as shoreline extraction, accuracy assessment, basin scale, mapping, beach slope estimation, and so on. Again, I am not familiar with this tool. There are commercial, workflows available also, such as the one developed by S3 Industries that is displayed here. It involves using machine learning and deep learning techniques for coastal line extraction, and it comes integrated with their marine module, basically, which is a paid, extension of their commercial software ArcGIS Pro. So you can look up and observe the video on YouTube, which is available, which contains the tutorial for this particular workflow as well. So these are some of the tools involved, and there is also one more, which is ShoreX. And endpoint rate tool is basically using ShoreX on a open source software, which is QGIS. EPR4Q was developed by Dr. Lucas Teres de Lima and his fellow researchers at Center for Environmental and Marine Studies in Portugal. This paper presents the efficacy of EPR4Q tool compared to other popular methods for coastline research, such as DSAS and UMBUR. While the former uses a commercial software, the latter is technically complex to operate. Hence, the need for developing this tool was felt. Overall, a high degree of correlation was observed between these methods, and this method is proven to be useful on linear, extensive, and non-extensive shorelines. Let me present to you the definition of endpoint rate. It is basically the mean annual rate of shoreline change in meters per year, and is calculated by dividing the distance of the shoreline movement by the time elapsed between the oldest and the most recent shoreline. A very complex looking methodology is basically the premise of the EPR4Q tool's algorithm. It involves the casting of the transects, calculating the beach angles, and creating buffers, and so on. So you can see the multiple, processing steps that are involved in analyzing the shoreline from this graph. As I had indicated previously, a high degree of correlation was observed between EPR4Q and the other two popularly used tools for doing shoreline analysis. one thing that I would like to highlight is that all these tools do not perform that well on embayed shorelines, which is basically this type of curved shoreline. It's basically difficult to cast transects and perform measurements on these types of shorelines, and I had wished I had known this fact, because I had racked my brain for hours if not days on a particular type of shoreline similar to embayed shoreline, which I will also demonstrate in brief later in this video workflow. That being said, this tool is completely free to use and open source so that it can be developed by researchers further, and I'll definitely recommend you to use it. Our area of interest is Satabhaya, and we had already done quantitative analysis for that, and we'll continue doing that using EPR4Q. And to do that, first we have to download the latest version. Currently it is version 3.4 of this tool. Can be downloaded from zenodo.org. Certain instructions also have been mentioned on how to install and what are the parameters involved. I have already downloaded this tool and extracted its contents. There are basically the model file as well as the symbology or the result, you can say, output design files. On YouTube, there is a tutorial developed by the founder researcher, Dr. Lima, and while it is narrated in Portuguese, you can also use the English subtitles. Nonetheless, one of the reasons behind using this tool is to present a English version of this particular tutorial and quite hands-on in that manner, so that it can be more accessible to enthusiasts and researchers. On ArcGIS Pro, the previous results are displayed over here. The Satabhaya shorelines from 2024 and 2020 are basically displayed, and I have used a beach extent, basically a 2 kilometer long polygon from the entire coastline. We'll restrict our analysis on that 2 kilometer stretch, which I had even used in the previous workflow. Satabhaya is kind of right middle at the bank of this particular extent. Now we already know that Satabhaya is very hardly hit by coastal erosion, and it kind of eases, gives us a perspective while we do our analysis. The measure distance tool indicates that the length of the chosen area of interest is just a shade under 2 kilometers or 2000 meters. While I will not be taking you through the steps that I had used to create this beach polygon, but just to highlight that I had done so by creating a new feature class in the default project database. The feature class was in a polygon shape, and upon creating it, I had manually drawn the beach polygon over the area of interest. And I'll use this particular feature to clip the existing two shorelines. I'll use the clip geoprocessing tool, and in the input feature or dataset, I'll select the shoreline from 2024 first, and under the clip features, I'll use the beach extent polygon. I'll repeat the same step on the shoreline from 2020 as well, and I have both the shorelines now available. Let me update the base map to the satellite imagery view. The red colored shoreline is the recent shoreline, while the blue colored shoreline is from 4 years prior. Now let's begin with the next step, which is to manually draw the reference lines or the baselines. One is on the landward side and the other one is on the seaward side. So let me begin by landward side. I'll create a new feature class, select line as the type of the feature, uncheck the z values because we do not need height attributes, leave the fields as default, and this is a very important step. We'll have to convert the default geographic coordinate system projection to a projected coordinate system, PCS. We'll use the UTM grid, which basically is in meters, and the way to identify can be several, but I'll use the snap tool, and in that I've uploaded as an input my existing satellite imagery, and using the reprojection tool, as I select UTM WGS 6084 automatic option, you can see at the downside of the screen, the CRS is updated to UTM zone 45. So I know that my area of interest lies in UTM zone 45. UTM stands for Universal Transverse Mercator. It's a commonly used projection system which is effective on geographic information systems. So I'll select the UTM zone 45 from the options available. because it is in the northern hemisphere, the zone is UTM zone 45N. So this is an important step, without which, if you don't do this step for all the layers, the EPR4Q tool will not operate function very well. So be very careful that you have to do this particular step. Subsequently, I will manually draw the landward side baseline. And once again, an important aspect is this particular baseline should be very, very close and run parallel to the shoreline. So it should not be at a large distance. So basically it's the inner edge of the beach, you can say. And another important aspect is that the endpoints, the starting as well as the ending points of this particular feature should extend beyond the area of interest shoreline, that is. So it should be very close to the shoreline and it should extend beyond on both the edges. These are the two important considerations which you should keep in mind while creating this particular feature. Subsequently, I'll repeat the same step and create a seaward, you can say, baseline reference line. So both these reference lines will be used as the base to basically cast transects onto both the shorelines from 2024 and 2020 respectively. So I've done this particular step in a fast forward mode. Ensure that you save the edits after creating this feature class. And the length of both the landward and seaward baseline should be similar, and both should be close to each other with the edges extending beyond the length of the shoreline. I will now use a different tool, QGIS, on which the model will run. And as I export it, while the seaward and landward features have been already reprojected onto a Universal Transverse Mercator or PCS, I'll just have to export the features as it is. But while exporting the default shorelines that we had extracted from SAET tool, we need to ensure that we update the environment under export features to the 45N Universal Transverse Mercator grid. So all the 4 layers, we only require 4 inputs: the historical shoreline, the current shoreline, and the 2 baselines. And all these 4 layers should basically be on the same output coordinate system. And I've used UTM zone 45N. One another important aspect is, as you can see in the attribute table, there is a beach code, a shape length in the shoreline, as well as on the landward and seaward we had kept it as default, so the shape length is there. Now another important consideration while running the EP4RQ tool is that all the attributes in all the 4 layers should be erased, and there should be just one, you can say, row which contains null data, you can say 0 data, and I'll show you the way to basically do so. Let me open QGIS 3.4.3 with GRASS 7.4.2 software version. Again, the preparation side of using this tool is very, very important, and I had racked my brain for hours, if not days, and even consulted Dr. Lima because I was facing errors in using this tool. So I received the indication that he had developed the tool on this particular format, on this particular, you can say, version of the software, and I am using the same version of the software. One can download this version freely from the QGIS website. And this is very important because the model seems to run the best, or you can say most effectively without any errors, on this particular version of the software. Once I have created a project file under the processing toolbox display of QGIS, I'll first of all load the downloaded model file. So I'll navigate to the folder where I had downloaded the algorithm and click on the model. So the model EPR4Q has been loaded. Just let me show you the graphical representation of the model, which I had also earlier shown you on the research paper. It's mentioned in Portuguese, but you can see that it's a massively, you can say, complex looking software. There are several processing steps involved, and Dr. Lima and his colleague researchers have developed this particular tool. One can, if one has the wherewithal, one can even edit this tool in the way one wants. Now this is not a mandatory step, but to be on a safer side, what you can do is install a particular QGIS plugin. Visit the plugin pane and search for processing Saga Next Gen provider. In case you are using QGIS version 3.4.3 as I have recommended, you will be offered to download Saga 7.2. Now this is what you should install, and subsequently also search for Saga 7.2 binaries on Google, and you will be redirected to sourceforge.net, from where you can extract the zip file of the binaries. Thereafter, you can extract the content of the zip file in a folder of your choice, and then under the processing toolbox in the options pane, go to providers and click on Saga NG, and in the Saga folder, link the path to the extracted folder. Now this step is mandatory, which is to go in the general section of the options pane, and under the invalid features filtering, just ensure that the ignore features with invalid geometry option is selected and not anything else. This is an absolutely mandatory, without which the model will not run properly. Now that we have more or less prepared the QGIS, we are now ready to do the processing. What we will do is the 4 inputs, both the shorelines and both the baselines. Let me add it to QGIS. I have a base map of OpenStreetMap. You can use any base map that you like. That's not relevant. Let me symbolize the baselines in a different way so that it can be distinguishable from the shorelines. Now, what we will do next is revise the attribute table. Go to the attribute table. You need to make an edit. We don't need these attributes. Delete all of them, as the model will not, will encounter an error if you run it in this way. Add a field and type ID with a capital I and a small d, and click OK. And in the ID, in the first row, type in 0. So essentially, you need to have only one column with the name ID, and within it, the value should be null or 0 basically. And you have to repeat the same steps for all the 4 layers. This is again an important step. Let me fast forward it. I have already done these following steps, and now all my 4 layers have only one attribute, which is ID with a value of 0. As you can see, both the baselines extend beyond the edges of the shoreline. And now we can click on EPR4Q model from the processing toolbox and ready to run the model. There are certain instructions which are mentioned on the right hand side, and you can basically have a look at it and then use the parameters to insert your inputs. I'll keep the default year to be simulated as 2100. The year of my oldest line is 2020. The left baseline on this particular map is the baseline on the land. So I'll click on the landward baseline. The space between points, I've used 7.5. The instructions are mentioned because I'm using Landsat imagery with a 30-meter resolution. So 7.5 or 5 can be used. So I'm using 7.5. The year of newest line is 2024. And I'll link the newest line. Beach angle is the angle of the beach. So this is a roughly 45-degree angle. You can insert this particular angle as per your area of interest. The right baseline is the seaward line, and I will link it. The oldest line is from 2020. In the final 3 inputs that we have to insert is result style final, result style left, and result style right. These are basically the symbology files. QGIS will render the output in a particular format, and these are the files. In the EPR4Q model, the 3 files are already there, and all you need to do is basically link the result files over here. Right. Now these are the only parameters that are needed. We are currently just saving the output as temporary layers. In case you want to save it permanently, you can just click and name and put the path to the destination folder. We are now ready to run the model. Depending on the size of the beach and the capacity of your system, this may take minutes to run. If you have set up QGIS and the layer files in a proper manner, you should not encounter any error while running the EPR4Q model. Occasionally, you may see some red colored warning messages in the log file pane, though you must not be worried about it. It's just something to be ignored. That being said, major errors occur if there is no output that is generated upon the model's completion, or if the model stops abruptly with an error message, or if the rendered output contains certain glaring errors or discrepancies that you can spot. Let me show you the output that has been generated for our model over the Satabhaya village. There is a visual output that has been generated alongside 6 temporary layers. The layers are result layer, the left side result, newest line, oldest line, right side result, and the points layer. Visually, it may appear overwhelming and complicated. It's not like that. To understand it better, let me switch off all the layers and turn it on one by one. The points layer, if you can see, lies exactly on top of the shoreline of 2024, which is the recent shoreline. The right side result are, you can say, some hilly kind of peaks towards the landward side. The oldest line is basically the transects cast from the seaward side baseline onto the 2020 shoreline. The newest line are the transects cast from the seaward line to the 2024 shoreline. The left side result contains a solitary peak but towards the seaward side. And the result layer contains all the transect information with certain color coding. So this is what the visual interpretation of it was. If you open the model again and refer the text mentioned against each of the generated output, there are a few lines written off for it, but mostly it does not make sense as it was translated from Portuguese. You can see in points though, it's important. The shapefile shows the space between points. This result is just to see if some error is there in the analysis. So this should basically get you started thinking, what does it essentially mean? So I prefer to use ArcGIS Pro for analysis and interpretation. So rather than doing it on QGIS, one can do it, but I prefer to do ArcGIS Pro. So if you see the points, there is a attribute table. There is a sum total of 253 points. Even there is a attribute table over here for the right result layer, and there are a lot of columns involved. So let me do one thing. Let me just, for the interpretation part, let me just export the layers. Currently these are in temporary form, so I have to make it permanent and save it as a shapefile, and then I will transfer it to ArcGIS Pro and explore them further and interpret them for you. So I just save it in the destination folder of my choice. I'll fast forward the entire process for all the 6 layers and just show you the output that I have generated, and let me load it onto ArcGIS Pro, all the 6 exported shapefiles. So the output has been generated and loaded onto the content pane of ArcGIS Pro. Let me symbolize it so that it can be interpreted better. So the right side result, which contains all the big peaks on the landward side, I've color coded it as red, whereas the solitary peak on the seaward side, I've color coded it as green. Now what we will do is categorize the layers. It is important to do so that you'll get a better perspective. All the result layers I have clubbed together on top of each other, whereas newest line, oldest line and points, I have kept it as a separate category. Now the reason why I do so is because these three layers, newest line, oldest line and points, serve as a validation, a check basically. And the other ones are for interpretation purposes. So if you see that there are equally spaced points and transects across the shoreline. So let me measure the distance between two transects. It is exactly 7.5 meters. Now you know already that the entire extent of the shoreline is roughly 2000 meters or 2 kilometers. So if I divide it by 7.5, so there should be at least, there should be roughly around 266 points, which we are basically measuring. So you can see there are 253 points. Our extent was slightly less than 2 kilometers. So there are total 253 points which are basically used for the measurement. If you compare it to the output of the previous workflow using the SAET tool, there were 10 segments of 200 meters each. So now it's a much more granular analysis from 200 meters each segment to a 7.5 meters each segment that will do the measurement. And which is why this tool is much more powerful. It gives a better reading, a better output and interpretation. Even the newest line and the oldest line, you just have to check whether they are equally spaced across it. Now you can see that there is a broken segment over here. But besides that, across the entire length of the shoreline, there are equally spaced segments, both the newest line as well as the oldest line. And just over here towards the end, there is a broken segment. And that is actually because the length of the baselines are not equal. There is a slight gap. And the length of the shoreline also, there is a slight gap, which is why the discrepancy, but it's not a major thing. One can, choose to ignore it. Although if you were to do scientific research, you should basically correct this error. That being said, what we will do now is to examine the attributes, which is the data stored in this layer. So this visual output is there, and one can explore the attributes now. If I open the attribute table of right side result, you can see that there are several columns. There are some total of 501 rows, which should surprise you because the number of points were 250. So this should trigger you that it's actually double counting. It's not exactly double counting, but currently it is not measuring the points data. It is measuring the transect data on both the shorelines. So which is why the 500 figure. And the only column of interest should be the hub distance, which is basically the distance of the transect from the baseline to the shoreline. So that is of the only interest, in my opinion, for this particular layer. Similarly, if you were to explore the attribute table of left side result for the small peaks, that is, there is only 2 rows with the same number of columns. And once again, only hub distance you can basically explore. The other columns are technically not of importance, just in case you want to measure the net change of between the coastlines. So these serve as just a visual output. The data attributes are not that important for these particular 2 layers. All the data attributes are actually, which are important to us, are present in the result layer. So you can see there are some total of 254 features, which is exactly the similar as the number of transects. There is one difference, but that was due to the anomaly. So this is the layer which basically contains the difference between the distance of the nearest hub between both the shorelines. So the distance, this DIST, DIF column shows the net erosion or the accretion in the across the transects. So if I sort it on a descending order, you can see that all the values are in positive and there is one value in negative. Ideally, you can multiply it by -1 so as to get the exact erosion and accretion, but I will leave it as it is. Just remember that the positive numbers are erosion because those are basically peering on the landward side, whereas the negative number, because it is jutting out on the seaward side, it is accretion. And these are predictions. So DIST diff is not prediction. So this is the net you can say erosion. So across the spectrum of the shoreline, 13.11 meters on an average is the level of erosion. The visual output, the large peaks that you see, are not related to DIST, DIF. It's basically the result column visualized, and it is because this tool has a analytical component. So you can see 250 meters is the average erosion across the spectrum of the shoreline in 2100, which was our future year of simulation in the model input parameters. So to approximately summarize the output of the EPR4Q model on Satabhaya in terms of the actual net shoreline change, 13 meters on an average per transect multiplied by 2000 meters long shoreline gives us 26,000 square meters or 0.026 square kilometers of net eroded area between the 3-year period of 2020 December and 2024 January. This is scary and should prompt the authorities to respond, because if the rate of erosion continues unabated, in 76 years from now, which is the year 2100, on an average, 500 meters per transect multiplied by 2000 meter long shoreline would translate to 100,000 square meters or 1 square kilometer of the Satabhaya coast to vanish into the sea. I'll switch to a different area of interest now, the Juhu beach in Mumbai, India, which is also reportedly suffering from high erosion. When I started working on the EPR4Q model, I began with Juhu beach as my initial area of interest only. Satabhaya occurred only as an afterthought after I had encountered errors while running the model in Juhu, and I felt I should repeat the new model over the previous area of interest from SAET and compare both the outputs. Hence, this last section of this workflow will delve into the challenges involved in running the EPR4Q model on certain types of shorelines and how to address it. Here on Google Map, I have zoomed into the western coast of India. In the bustling metropolis of Mumbai lies the very popular Juhu beach. It's a 6-kilometer long shoreline. I have already set up the project on ArcGIS Pro, and I will show you the results of the model on this software itself. What you can see are the two shorelines of Juhu beach, which I have extracted from the SAET workflow. The recent shoreline is from 2024, from 22nd of March, and the older shoreline is from 28th of March 2023. So they are just 1 year apart. Let me color the newer shoreline in red. So you can see that visually there is a discernible erosion on the coastline, as was reported in the various news articles that I had initially showed you in this video. Now I have already run the model on QGIS, and for that, remember that we have to export it, convert the projection into the PCS, projected coordinate system of UTM-43N, and subsequently also draw the landward and seaward baselines. So I have already run this output, and I'll show you how the whatever the parameters that I have inserted. So I left the year to be simulated default as 2100. Here, the baseline towards the left this time is the seaward line. The space between transects is 7.5 meters. And the beach angle this time around, I have inserted based on my, you can say, gumption, a 100-degree angle. Rest all things are naturally understandable, so I'll not explain it. Just I've saved the output as shapefiles and have imported it into ArcGIS Pro. So let's begin by seeing whether the model has visually generated proper output. So the points layer appears to be reasonably well rendered. There is equal spaces between the points across the shoreline. Let's see the transects, whether they are proper. The edge over here has several lines which do not meet the shoreline. So that seems to be a important problem. Apart from that, on the other edge of the shoreline also, there is several, at least 20 to 25 transects which do not meet the shoreline. So the output will get distorted because of it, and this working of the model is not useful for scientific research purposes. So in comparison, see the Satabhaya coastline. It was a linear shoreline and the transects were, besides one or two points, it was very well rendered. But over here, the output is not correct. So this is the first level of check where we visually see the newest line points and the oldest line layers. Even in the results section, let me show you a particular aspect. So the distance difference shows you the difference between the older shoreline and the newer shoreline. So this particular point, it is okay. But then if I were to show you another transect, you can see that it does not even touch the shoreline. It is just lying on the satellite imagery on the urban area itself. So the values are distorted and it would not be a good idea to see the statistics and understand what is the level of erosion. It may give you a good idea, but it's not a accurate idea. And the worst result of them all is the output of the projections. So this is how the left side and the right side results have been rendered. So right side this time, because the orientation of this, it's on the west coast with the ocean on the west. So the left side result is erosion and right side result is, which is purple in color, is the accretion. So you can see there is a huge levels of erosion which is displayed, and it's not tallying with the shorelines because the current difference between the shorelines is very less, but the levels of erosion which has been projected are very high. So it does not appear properly, and even the angular representation of the erosion and accretion is not proper. So this is, you can say, problematic. We cannot hold the output of this particular model as a proper output or an important output. So I had actually reached out to Dr. Lucas Lima, the creator of this model and this fellow scientific researcher. So he suggested that I should break down Juhu Beach into three different segments and run it as three different projects. Also, I should draw the landward and seaward baselines very close to the shorelines. And we have had several interactions because I was working on this particular challenge for days, and he kind of gave me some other solution also, just like to extend the shoreline and so on. But then I tried the first suggestion of his, which is to split, because this is a curved shoreline. So there is already, we had seen that this model does not run very well on embayed or curved shorelines. So I had to basically split it into three equal segments. Not equal segments, three segments, which has similar, you can say, angular properties of the beach. And I have done so. So I have split into split 0, 1 and 2. So these are the three segments I have divided my project into. So you can see this particular number 0 is the central side of the Juhu Beach. Split number 1 project is on the top side of the Juhu Beach, whereas the split number 2 project is the bottom side of the Juhu Beach. So I have split the entire shoreline into three parts and have also created baselines separately, with ensuring that it runs, you can say, as parallel to the shoreline as possible, and also extend both the ends on both the sides extend much ahead of the shoreline as well. Also, I have created it using the create function. I am not showing it to you, and I had split the shorelines using the split function. I had already covered these tools in my previous workflows. So these were the tools by which I had made the amendment, edit basically. Also, remember that I had converted all the shape files into the UTM zone 43N. This is the UTM zone of Mumbai. So now let's see how the revised output of the EPR4Q model is represented. So I'll begin with project number 0, which is on the central side of Juhu Beach. So this is the baseline. Let me show you the output after just editing the symbology. The red line is the recent shoreline from 2024, whereas the green line is the older shoreline from 2023. The points layer, let me zoom in. You can see that those are equally spaced across the length of the shoreline. So this is the first level of check, that our output that has been rendered by the model does not have any errors. The second level of check is to see the newest line and the oldest line. So you can see that barring the 2 or 3 lines in the end and a couple of lines in the middle, the transects have been spaced properly and run throughout the entire extent of the shoreline. Even the oldest line, it is similar to the newest line, with barring a minor exceptions, the output has been generated properly. Therefore, we can see the statistics on result _0 and assess whether what is the level of erosion or accretion on this extent of the beach. 13 meters of erosion has been witnessed in this beach, and that's a very high figure. So Satabhaya had 13 meters for a period of 4 years, from 2020 to 2024, 3 years rather. But then this one is within 1 year. There is on an average across the 6 kilometer long beach, per point there is a 13 meter of erosion, and at the most extreme it is 50 meters and 60 meters. Now I haven't factored in the tides while capturing, using the satellite imagery. So to not, you can say the output may be misrepresented, but the rendition of the model is not incorrect. So you can see. So I have validated also by clicking on the attribute. It shows me that the highest diff, which is 58 meters, is on the point where I had shown you where the maximum erosion was. So the rendition of the output is correct, and the right side and left side result, the blue colored ones are accretion. So you can clearly see that the recent shoreline extends beyond the previous shoreline. So it is a good candidate for accretion over the long term projection. So even at this end may be slightly debatable, but then beyond that, even the red line, which is erosion, it seems reasonably accurate. Although in Satabhaya we had a very high degree of projection, like 500 meters of erosion in 74 years, but this time around it is just showing 26 meters of erosion. So I don't know how it has been computed, but then it doesn't seem too far-fetched. So that is the case. So this was, I showed you how to basically address the issue, but then the central section, the output worked fine. But then let's see how it fared against the lower section of Juhu Beach, because this one is not a linear, it's a non-linear shoreline. It also has a certain curve attached to it, and I tried my best to basically create the baselines parallel to it. But let's see the output of the model. You can straight away see that there are big gaps in the points which have been created. So it kind of gives us a clue that not all is well in the output. Even the newest lines, it mimics the points. So the gaps are very well evident, and likewise for the oldest line as well. So this is a challenge of using the model. So while it works on non-linear shorelines, you need to basically create linear patches of shoreline and then run the model, which would give you the best output. The output is better than the original, you can say, default model, without the splits, but then it's not the most accurate output you'll ever see on this model. So that is about it. And if I see the left side result and right side result, you can see it's not looking very good. The angle is different. So in the beach parameters, on the model parameters, we have to also enter the angle of the beach. So I think the problem also lies there, because the beach is not in a straight line. So it's difficult to find the exact angle at which the model should compute. So this is another challenge. And I believe that to address this, make a better output, you have to split this lower section of the beach into other 3 parts. So in the research paper, Dr. Lima and his colleagues also had problems with embayed shorelines. I'll just show you that section, and they had also proposed how it could be resolved, although I could not understand the meaning of it, but then they did propose in this section problems usage of near and filter transect methods to adjust transects to curved shoreline segments. So they proposed workaround, but they recognize that the model is not working very properly on the embayed shorelines. So yes, this was a particular section on Juhu Beach, which I had wrecked days on, and I thought I'll just share it with you.